Welcome to our channel. This is a set of lectures that covers the entire Structural Design to Eurocodes course. There are 26 lectures, totaling over 20 hours of learning. We strongly recommend following the lectures sequentially to better understand and apply the course content. For easy navigation, there's a link in the top right corner of this video. By the end of the course, you'll have enough knowledge to handle basic structural design tasks using Eurocodes. With experience, you can further develop your skills as a structural engineer. Now, let's get into Lecture 3, Flexural Design and Material Properties. Material properties, reinforced and pre-stressed concrete beams, reinforced concrete columns, brittle failure of pre-stressed members. Before we delve into the lecture, please hit the like button and subscribe to our channel. Your support means a lot to us. Now, let's learn together.
Okay, so what we're going to cover here is the flexural design of reinforced concrete and pre-stressed concrete as well, but it's basically the same. No real distinction in the Eurocodes between pre-stressed concrete and ordinary reinforced concrete. That's one of the things you'll see time and time again in both Eurocode 2 and Eurocode 3. The Eurocodes deal with phenomena not by element basis, so we don't tend to have sections that break down into sort of slabs, beams, columns. It deals with everything in terms of behaviour. So you have sections on bending, shear, torsion, which is generally quite helpful, because you then get this sort of distinction between when is a beam a column and when is a column a beam. It's just basically something with axial load and bending in it, so we don't end up with this terrible distinction about which clause to use a lot of the time. So specifically what we're going to do is look at material properties in the Eurocodes. Then we're going to look at reinforced concrete beams and very quickly how that's modified for pre-stressed concrete beams. I want to say very little at all about reinforced concrete columns, because really they're too difficult to do by hand. You need some software. But that's no different from what it was previously. It's difficult to do calculations on columns. And then very quickly, just a few thoughts about a new check which we have to do for pre-stressed concrete members, brittle failure. In terms of material properties, for those of you completely new to Eurocodes, first most important thing to notice with the Eurocode 2 is that all the calculations are done with cylinder strength and not cube strength. So since cylinder strength is approximately 80% of cube strength, that's a serious mistake if you start using cubes instead of cylinders. Having said that, we still specify concrete the same way as we do now in terms of both cylinder and concrete. So a C40-50 concrete still means that it has a 40 cylinder strength and a 50 MPa cube strength. And the method of actually testing the concrete is up to you or the contractor, whether you use a cylinder or a cube. The other useful thing in the Eurocodes is that they cover, or the formulae work can be used for concretes which are much higher strength than they could do previously in BS5 100. So for buildings, the formulae can be used up to C90 105, and for bridges they can be used up to a C70 85. And the difference is just a bit of caution creeping in again in the bridges community, because there isn't so much testing on large-scale bridge-size members as there is with building-size members. The UK National Annex puts a cap in a couple of places on that, or well, specifically one place, when you're considering the shear resistance of sections without shear links in, the basic shear resistance. We mustn't use a concrete grade greater than C50-60 in the calculations. We can use higher concrete grades, but we can't take advantage of them in the calculations, which is due to some concerns with high-strength aggregates, which were there previously. They're not new, but we've just reflected that in the National Annex. Similarly for bridge works, the minimum grade that we're supposed to use the rules for is a C25-30. Well, that clearly doesn't apply to things like blinding, but for structural concrete, we shouldn't be using less than a C25-30. Very specific points, but in terms of the E value, in BS500 is a table. In the Eurocode there is a table, but in most situations there's a formula. All the Eurocode has been written around trying to eliminate the need to sort of look things up in graphs and tables. And I think they've done that everywhere, so there will always be a formula for something like that. And the value for the Young's modulus for concrete, the mean value, is a function of FCK, the characteristic cylinder strength. This is a big table, table 3.1, where you will find the formulae for a lot of these things, a lot of these different terms, but you will also find some numerical values. And you will find yourself coming into this table quite a lot when you do your calculations. So it contains information for different FCKs, which is the cylinder strength. It contains the equivalent cube strength, but then it also contains things like the mean concrete strength, the mean tensile strength, the 5% lower fractile tensile strength, the 5% upper fractile strength. Some of these you need, some of these you don't. I mean, for example, the lower 5% fractile strength you do use in calculations of lap length, because you're interested in tensile strength when you're calculating lap length. The remaining numbers down here, all these epsilon C1s, epsilon CU1s and CU2s, all relate to the different Flexural Design stress blocks that you can use, and there's 3 different stress blocks you can use, and these really relate to the 3 different blocks, so you find yourself having to come back to these. In terms of how you convert from characteristic strength to design strength, reinforcement, basically the characteristic strength is, for normal reinforcements, 500 MPa. Eurocodes don't cover plain round mild steel bars anymore. Can't use them, not the Eurocode rules. Design strength you obtain from the characteristic strength by dividing through by gamma S. Gamma S is recommended to be 1.15, and the UK adopts 1.15. So basically the same material factors as we have now. For pre-stress, again, we'll see the stress strain curve for pre-stress in a minute, but one of the parameters for pre-stressing is the 0.1% proof stress, which is the nearest equivalent to yield in pre-stressing. And again, we'd get the design value by dividing by gamma S, again 1.15. Most significant one really is for concrete. So the characteristic strength, the cylinder strength is FCK, but the design concrete strength that we use in calculations, whether this be bending or shear or torsion or strut and tie, the design strength FCB is the characteristic strength divided by the material factor gamma C, which is 1.5, as it is in BS500, but it's also multiplied by a factor alpha CC. And alpha CC is an annoying factor because it changes value in different calculations. So for bending, it's 0.85. For shear, it's 1.0. And those 2 distinctions really reflect just what numbers we used in the initial calibration of the load model, of the resistance models that we use. So it's just a bit unfortunate. That's pretty much all the Eurocode itself says. It says for bending it's 0.85, and for shear it's 1. But when you get into other things like strut and tie, we think, well, is that bending or is it shear? Or because it depends what you're doing. So to make it fully consistent, what the UK National Annex has done is it's gone through and listed out what the value is in each clause. And if you want to know why it's ended up the way it is, there's quite a long section in the Thomas Delford guide about why it's sort of 0.85 in some places and 1 in others. And we'll probably try and pick those up as we go through some of the different checks like shear and torsion. We'll probably pick up what value it is here and why as we go through. But beware of it, because this is another pitfall in the spreadsheet. If you have FCD in there, it might not be the same for shear and for bending. Reinforcement we now specify to EN 10080, but we've effectively been doing this for some time now anyway through the existing BS. So bars can have 3 different ductility types, A, B or C, and A is the most brittle type of reinforcement and it's not allowed basically. B is what you tend to typically get as normal reinforcement. The standard designation used in the Eurocode is the one here. So if you put B 500B, it means you're going to get a B for a bar. 500 is the yield strength of the bar, 500, and then the number at the end is the ductility class. This is quite important. When we do our flexural design, we have a choice of 2 stress strain curves that we can use for reinforcement. So ignore the dashed one, which is as one factor the characteristic line, and just look at the solid ones. We've got a choice. We can either use a curve that has a linear elastic up to design yield, FYD, and then a horizontal line, which is pretty much what we've done in BS500. And if we use that, there is no check whatsoever on reinforcement fracture. We can just strain it forever, even though in theory it will actually fracture at some point. Alternatively, we can use a second diagram which has linear elastic up to yield, but then it has a rising branch which goes up to the ultimate tensile strength of the reinforcement. And we can use that, so we can take benefit of the reserve of strength beyond yields. But if we do that, then we have to make sure in our analysis of the section that the strain in the reinforcement doesn't exceed the fracture strain. And that's basically what epsilon UD is. It's 0.9 times the characteristic fracture strain. So if we do that, we really have to use a sort of strain compatibility type analysis and actually physically check what the strain in the reinforcement is. Once again, if you're working for contractors, we're probably going to be doing all our calculations using sort of SAM or something like that anyway. So there's really no point selecting the simple stress block. We may as well use the one with the rising branch because it will bring you some economy normally. I think there's a numerical example coming up. But for ductility class B reinforcement than normal, if you've got normally relatively low reinforced sections, it will give you 7% more bending resistance than the horizontal line width. So it's just 7% for nothing. Really. Pre-stressing in the Eurocodes is specified to EN 10138, which is not yet published due to various arguments across Europe. So at the moment, for specifying pre-stressing steel, we carry on specifying to the existing BS, whose number I can't recall. but basically the existing BS and the EN are pretty much aligned anyway, so there's no real significant differences. When the EN eventually comes out, it will identify 3 classes of steel in terms of their relaxation at 1,000 hours. So class 2 is basically normal low relaxation pre-stressing strand that we use day to day now. 1 is for ordinary pre-stressing strand, which has a much higher relaxation at 1,000 hours. And then there's a separate classification for bars rather than strand. And the designation for pre-stressing steel is similar to that that's used for reinforcement. So Y basically denotes its pre-stressing. 1860 is the ultimate tensile strength of the pre-stressing. S7 just means it's a 7-wire strand pre-stressing steel, and then the 15.7 gives you the strand diameter. So it's quite a helpful designation because you can see what you've got just by looking at it rather than some sort of arbitrary definition. And the design curves for pre-stressing they look the same as they do for reinforcement. There's a subtle difference though compared to BS500, or not so subtle, but you just don't notice it until you look carefully at it, which is, again, we have a horizontal branch version or one with a rising branch. But in this case, if we actually want to get an answer which is as economic as BS500, we have to use the rising branch. Because in BS500, the horizontal branch wasn't at yield, or the 0.1% proof stress, it was actually at the ultimate tensile strength of the steel already. The justification has always been slightly iffy. So with pre-stressing, again, choice of 2 options, either a flat branch at the 0.1% proof stress or a rising branch up to ultimate tensile strength. And if you use the ultimate tensile strength, you have to check, again, the fracture of the pre-stressing steel. In terms of creep and shrinkage, we'll see a lot more of this tomorrow when we do pre-stressing. But it's unfortunately treated in a much more rigorous way than it was in BS500. So unfortunately, gone are the days where we can just say, well, here's the short-term E value, and the long-term modular for dead load is just half of that. Well, you could do that, but you're just making up a number. What we're supposed to do is calculate the creep strain directly from the elastic strain multiplied by creep factor. So if we want the long-term modulus for a particular situation, then we need to work out what the creep factor is for that particular situation. And the creep factor will depend on things like the age when you first loaded the structure, the thickness of the component, because that affects the rate at which moisture can get in and out of the section, the composition of the concrete, cement and water ratio, these sorts of things. Having said all that, if you do all these numbers for normal concretes, then you just normally find that the long-term value of phi is around about 2 anyway. If it's not 2, if it's drastically different from 2, you've probably made a mistake, which then means that the long-term modulus of short-term divided by 1 plus phi is normally a third. So long-term, the value is a bit softer normally in the Eurocode than it was previously in BS500. Shrinkage is the same. We haven't got a nice simple value. Like we previously used to have sort of 200s. Microstrain, I think, is a shrinkage value for typical concretes. Again, in the Eurocode, we have to work that out from composition of the concrete and the section dimensions. It's not difficult, but it's just something else to do. And you'll find that you have to calculate 2 components of shrinkage separately and add them together to get your total shrinkage. And just so you know what they mean, there are 2 components. There's a drying shrinkage, which is probably what we mostly think of as shrinkage. That's, as it sounds, is with time water moving out of the concrete and drying. But there's also an autogenous shrinkage term, which occurs generally very quickly over the first few days. And that's basically water being absorbed in the chemical setting reaction. So the water doesn't actually migrate out of the section, it's being consumed internally. But both of those lead to shrinkage, but with different durations of time. So specifically onto bending, we have 3 allowable stress blocks that you can use. There's a rectangular block, which isn't quite the same as BS500, because you'll find that the stress limit is slightly higher, and also it only extends down 80% of the way to the neutral axis, rather than all the way down to the neutral axis. But the practical significance of that is nothing. There is a rectangle parabola diagram, which is the same shape as the BS500 one, and there's an additional triangular one. In terms of the order of which gives you the best answer, by best I mean kind of the most economic answer, the rectangle gives you the most economic, which is not the same way around as BS500, where the rectangle parabola gave you the best answer. So the most economic is the rectangle, the second most economic is the rectangle parabola, and in last place is the triangular one. So it's completely pointless ever using the triangular one, and it's pretty pointless ever using the rectangle parabola one as well, because it's more complicated, it doesn't lend itself to any hand calculations, and you won't get as good an answer. The reason for that is founded in error. There was actually intention to put a small reduction factor on the FCD value for the rectangular block, but it was omitted in the drafting. And when it was kind of spotted sort of later on, they realised actually the difference between these two was only ever about 1 or 2%. So just to keep it nice and simple and not have extra factors knocking around on different blocks, they just left it like that. But that's why this one will always be slightly more economic. You've got a lot of difficulty convincing software houses that's the case, so they spend ages trying to implement the rectangle parabola one, but it's not very much point. Just before I just say something quickly about that stress distribution, the other thing is that there is no formulae given for bending in the Eurocodes. So we'll talk about that. There is a formula presented on one of these slides, but it doesn't give you any formulae. So really you are quite dependent on using software or simple formulae that somebody else has given to you. I recommend using the computer, to be honest with you. All this slide shows is just the different blocks sort of drawn out. So, for example, the rectangle parabola block, the start of the flat portion of the curve starts at epsilon C2, and it finishes at epsilon CU2, and those two strain limits are given to you in that big table I talked about at the start, table 3.1. So the rectangular block uses EC2 and ECU2. The bilinear distribution and the rectangular one use EC3 and ECU3, and they're actually, I think the lower grade concretes are the same. It's when you get to high grade concretes they start to differ in value. And if you plot the three stress blocks out on top of each other, the rectangle parabola, the linear one and the rectangular one, it kind of becomes obvious why the rectangular one is more economic. Because in this particular case the rectangular block and the parabolic one have got pretty much the same area to the same force, but the centre of gravity of the rectangular one is obviously slightly nearer the outside of the section, and therefore gives you a slightly better lever arm, and therefore gives you a slightly better answer. So that's all kind of the material background. So in terms of calculating a bending resistance, that's pretty much all the Eurocode gives you, is contained on that slide. So it just good old-fashioned engineers sort of theory back to university. It tells you the plane sections remain plane. It tells you that the strain in the reinforcement is equal to the strain in the concrete if you've got bonded reinforcement. It tells you to ignore the tensile strength of the concrete in flexural calculations. And if you've got pre-stressed steel, then it tells you to take into consideration the pre-strain in the analysis. That's pretty much all it gives you. I don't want to go into any detail in this because it's not. I think it lacks practicality really, because the reality is that we will be using the computer rather than trying to do strain compatibility by hand. But all this slide is really saying is if you haven't got a computer and you're not going to use one of the simple formulae that I'm going to put up in a minute, then that's what you've got to do, an iterative procedure that will locate the neutral axis, check the forces in the steel and the concrete match if they don't go round and round again. So, just before I put up a simple formula, there's one other thing just to baffle you with, and then you can probably largely ignore it, having hopefully understood what it's supposed to be doing. You'll find that there's in the clause we were just talking about that lists out the assumptions, it talks about in some situations you may not be able to actually get to the full strain limit of ECU2. ECU2, by the way, is the sort of 3.5 millistrain, the same sort of number that we have previously in the British code, for reinforcements up to, I think, 50, 60. Below that it starts to drop. But it warns you that if you've got an overall stress diagram that's got a combination of axial force and bending, you may not be able to get up to the full ECU2 load. And the reason for that is if this is our idealized diagram shown here based on the rectangle parabola diagram, what the concrete actually does is the dashed diagram. So it will actually overshoot the strength at some point, but towards failure the stress will actually drop off. It won't stay horizontal as in the assumed curve. So if we actually look at ultimate failure, ECU2, the real behavior actually has a limiting stress that's lower than the idealized behavior. But if we go back to the smaller strains, EC2 for example, then the real behavior actually has a stress which is much greater than the idealized behavior. So what this is potentially saying is if your section is in bending, then the real distribution across the cross section will not be the idealized one, it will be the real one. But it doesn't really matter that the stress at the outer fibre is lower than you're assuming, because the stress slightly further in is actually much greater. So it's the overall net effect is actually you've got more concrete force there than you think. So if your section is in bending, the idealization is fine. If your section is in pure axial force, there's no bending at all, it's just simply vertical force, then at the actual final crushing strength, if you actually were to get to ECU2, you actually find you're overestimating the force, because everything is actually down here on the dashed line and not on the on the solid line. So if you were able to strain it to that level, then potentially it's unsafe. So this makes life difficult. We didn't worry about this previously in the good old-fashioned BS500. What it actually says is if you have sections which are in overall compression with some bending, or even if you have flange outstands which are wholly in compression with some bending, then you have to kind of work to a new stress limit. And this picture is trying to show what you have to work through. So if this is a flange which is wholly in compression, it tells you that you have to work at heights, if the flange thickness is height h, and we have these two strain limits, epsilon C2 and epsilon Cu2, then we have to calculate a height in the flange equal to the height times epsilon C2 over ECU2. And at that point, the strain mustn't exceed epsilon C2. So we're not actually anymore checking at the extreme fibre, we're checking at this fictitious point. And what that means, it kind of defines a pivot at that point there. And if I go from one extreme where the whole flange is completely in compression, then it means that the whole stress limit for the whole flange is epsilon C2, i.e. this point over here. At the other extreme, if the section has got zero force, zero strain at one fibre and full strain at the other fibre, then we pivot around that pivot point down to zero, and that means if I draw a line from zero strain through the pivot, then I actually achieve at the extreme fibre a strain limit of epsilon Cu2, which is what we've conventionally used before. And any strain in between that, as soon as the whole structure is in compression, basically my extreme, as the compression increases, my extreme allowable fibre stress reduces from ECU2 about this pivot point down to EC2. There's lots of blank faces there, I'm sure. But that's what it's trying to do, is safeguard against this potential problem here. Now, most software packages can't do this because it applies not only to the overall section, but also, as I say, to flanges and outstands, and there's not enough sophistication in the package to actually know which bit is an outstand. So most of them haven't implemented this at all, as far as I know. And we've done some trial calculations on it, and I haven't found this actually make any difference by more than about 1 or 2%. Now, I personally think that effect is mocked up in the alpha CC factor. I think it's quite safe to include it in there. And so I wouldn't personally worry if all of us just completely ignore this, this sophistication, and just do what we've always done before and just work to ECU2 with that diagram there and not worry about sort of stopping the analysis here. But just be aware, that's what it's talking about. It's trying to prevent this situation of potentially, if the stress is just completely compressive, ending up on ECU2 is unsafe. And now forget it. Right. Just for the purpose of the notes, really, again, I say I think we should use computers. And Sam will do these analyses for us. But just for the purpose of the notes, what you have on the slides and also in the book are some sort of simpler ways of trying to calculate things by hand. And you'll find that a useful parameter in the notes is basically the force FC being made up of a function of the neutral axis depth x and the average stress FAB in the compression area. And FAB, the average stress in the compression area, is a function of the different stress blocks that we have. So in the notes, this is a horrible formula here for what FAB is for a rectangle parabola block, a bilinear block, and a simplified rectangular block. And these can be used to basically work out your flexural design. I would ignore all of that complexity and just stick to this one slide, basically. This is the only thing I think is actually worthwhile ever doing by hand. And this is if you just want a really, really quick, rough and ready estimate of the bending resistance of a section. You can do this by hand. Anything else, you're really going to need to do something else by computer. Use the rectangle parabola. Sorry, use the simple rectangular stress block. The rectangular stress block is such that it has a depth lambda times x, and the code tells you that lambda is 0.8. That's why I said it extends 80% of the way down to the neutral axis. So clearly, because it's just a rectangle, the centre of force FC is in the middle of that rectangle, 0.4x down. The stress block itself is eta times FCD, but as I mentioned, eta has been set as 1.0, other than for very high strength concrete. So I think for above a 50-60, I think eta starts to drop down smaller. If we know that simple diagram there, we can very easily just balance the forces in the concrete against the forces in the reinforcement, and we can produce a simple bending resistance formula. So we have the bending resistance is just the steel area times the yield strength times the lever arm, where lever arm is this function of the stress block here. So that there's nothing else to calculate other than functions of the stress block. If we do that, that obviously assumes that the steel yields. We've had to assume that. So we need to just check that it does actually yield. And this second formula here is basically just looking at this strain diagram, and for the neutral axis depth we've got, assuming the concrete is crushing at epsilon Cu3, the limit for the concrete, it does the reinforcement actually reach yield, Fyk over gamma s, divided by the E value. And so that's a criteria for whether it yields or not. If that's satisfied, then that formula is okay. If it's not satisfied, then the formula isn't okay. And just as simple as that. You have to go and do something else. In the workshop in a minute, there's just an opportunity just to use that very simple formula, because to be honest, that's all we can really do by hand. And then there's a secondary example if there's time, which looks a hell of a more complicated for a piece of pre-stressing. But most of the numbers are filled in, so it's just about going through the process of calculating. The reason for defining the average stress FAV in the compression block and beta, which is the centroid of gravity in the compression block, is if you don't want to design based on basically guessing reinforcement, calculating a bending resistance and comparing it to the applied bending moment, they don't match, so you have another guess at the reinforcement. If you want to do it the other way around and actually work directly from the bending moment to design the reinforcement area, then there's a set of equations again in the notes that allow you to do that, and you basically just have to solve for the neutral axis depth, and then that gives you the area, and then just check the reinforcement yields. To be honest, it's easier just to guess the reinforcement and try that way around. Just a quick numerical example. This just literally gives you the results rather than actually sort of takes you through the calculations, but for a very, very simple rectangular beam with B500B reinforcement, ductility class B rebar, alpha CC is 0.85 for bending. The two material factors there. What results do we get for 20 diameter reinforcement? Well, if we take the horizontal branch curve, which we can use that simple formula for, then we'll get 1354 as a bending resistance, and I think that's what you actually do, basically determine that in the notes in the next workshop section. If you repeat it with the rising branch, which then doesn't lend itself to a hand calculation because it becomes iterative, then your bending resistance increases to 1449, so that's a 7% improvement, which is what I keep saying. You're better off using the computer. And if we compare it with, we compare those two numbers, the rising branch, the flat branch, and what we used to get from BS500, even if we use the flat branch, we have a slight improvement over BS500 in this case, which is just a quirk of the two codes. In BS500, the lever arm was limited to be 0.95D and not bigger. In this particular example, the lever arm comes out as 0.97D, and there's no limitation on lever arm. I think this is. I'm going to just jump over, I think, these next slides because it's just going into too much detail, considering I keep saying use the computer. So the notes, again, do give you means of tackling doubly reinforced sections by hand using the same sort of methodology, but I think that's probably too much detail, so I'll just jump over those. The last thing I think to say about reinforced concrete really is what happens if you've got flanged beams, because the formula we just derived there was really just for a rectangle. And basically, as long as your flanged beam, you can prove that the neutral axis depth you calculated still lies within the flange, so that the width of concrete B is constant, then you can still use the same formula for bending that we use with a rectangular beam, because you just basically have one dimension of B. If your neutral axis ends up with the top flange in compression, but the neutral axis is some way down in the web, so we've got obviously then two width dimensions to play with, then you can't use the simple formula because it's only catering for one width dimension. So it's pretty obvious stuff. But I think generally you find with flanged beams like that, the neutral axis normally does occur in the flange, so it's not really much of a limitation. If we move on to pre-stressing, there's an example in the notes, so I'm not going to say too much about this either. The only real significance or difference, we still have to use the same stress strain blocks, but we have to calculate what the pre-strain is, and that the pre-strain basically comes from the pre-stress after all losses multiplied by a gamma factor as well, the ultimate limit state gamma factor, which is less than 1 for pre-stressing force. So that allows us to calculate pre-strain, and then when we come to look at our stress strain diagram and we check whether pre-stressing is yielding, we have to take account of the fact that we've already got a certain amount of strain in the pre-stressing. And so as an example, we'll pick up how to do that. Columns, so I'm not going to say anything in detail about columns. The same rules apply. That horrible diagram with the pivot point that we mentioned about applies in that situation, but as I mentioned, it doesn't make much difference, so I'm personally quite comfortable about ignoring that particular provision. Other things to know, probably notes, are that there are some minimum moments we have to consider in the design of columns. So whatever bending effects we derive in the columns, we shouldn't take a moment that's less than that due to the minimum eccentricities given here. So we should at least consider an eccentricity of 20 mil or height over 30 as an eccentricity in load position. That's in addition to the eccentricities from overall column lean that we talked about. So you'd have to add that in as well. But generally that's pretty small, as I said, for normal motorway bridges. And the other thing we have to take into account, obviously, is slenderness. If the columns are slender, then we either have to add in some slenderness extra moments, or we do a nonlinear analysis to include that. Okay, I think the last thing I want to mention is just brittle failure in prestressed beams, because this is something new. Generally, I don't think it will actually contribute any additional reinforcement or anything if you do the check, depending on which check you do, unfortunately. What this is supposed to be around, there was some concern that what could be happening with a prestressed beam is you may well have the tendons in there stressed and corrosion is going on and you don't know about it, and the wires are busy breaking and deteriorating. But actually your traffic is relatively light, and although all these pre-stressing strands are going, the beam is actually just standing up on its tensile strength, the combination of the tensile strength and a bit of pre-compression. The concern is if that's going on, that suddenly you get a bigger load and the tensile strength is lost and you've lost so much pre-stress that suddenly all the pre-stress fractures and the whole thing just collapses in a brittle manner. Now, again, it's another one we haven't really worried about too much. It only seems to be a problem if you have very large cross-sections with very, very light pre-stressing. So it's almost like a combination, it's just an unrealistic design. You know, a very, very big cross-section with very, very small pre-stressing in it, where that could potentially happen. But to guard against this anyway, there are three methods. Method C is basically the simplest one. This is basically inspect your structure for that sort of problem. But the only real way you can do that is to provide external tendons, so you actually physically go and look at them. So if you've got internally bonded tendons, method C is not possible. Method A is the one that really generally leads to no change to the design. It's the most efficient, but it's the most calculation work. And there's again, if you go into those books or to the notes online, there's an example of how you do the calculation if you want to. But what you're supposed to do is you consider the frequent load combination, and you work out how much pre-stressing you would have to lose through corrosion or whatever until, under that frequent load combination, the section basically first cracked and you exceeded the tensile strength of the concrete. And then under that same load combination, you then have to check that there is enough, having lost the tensile strength of the concrete, there is enough resistance in the remaining pre-stressing in the concrete at the ultimate limit state to carry that same load combination. So it's pretty bloody obvious, really. It's just saying to work out for a given load case, work out how many tendons you're going to lose, you would have to lose for it to crack, then assume that happens, and does it still stand up once it's cracked and you've lost the tensile strength. If you do that, as I say, you can almost always prove that it's fine. As I say, if you've got very little pre-stress and very large section, then basically what you're doing is when the concrete cracks, you've lost most of its capacity and there's virtually nothing left in the pre-stressing, so it might fail at the ultimate. If you don't want to do that calculation, then you have to put in more longitudinal reinforcement, basically, and there is a penalty involved in that because you have to put in as much reinforcement to basically fully cater for the loss of tensile strength, so you will end up putting more bars in there. So it's best to use method A.
Congratulations! You've completed this lecture. Keep up the good work by moving on to the next one in the series. You'll find the link in the top right corner of this video.